Chapter 3 is on chemical bonds, which is how atoms are bonded together in a molecule. Ionic bonds are between ions of opposite charges. It's the attraction between these opposite charged ions that holds your compound together and forms the bond. So if we look at a sodium atom, this is showing us our core electrons and our valence electrons. And we have one valence electron in sodium. This is showing us an atom of chlorine, and again, this is showing us the core electrons or the inner electrons and the valence electrons, which in this case we have 7 valence electrons. This diagram below here shows just the valence electrons. And the reason this is important is whenever you have ionic bonds form or you're forming ions, it's always going to be just your valence electrons. The core electrons are not going to be changing, so we don't have to represent them in the picture here. So sodium, again, wants to have 8, so the easiest thing for it to do is to lose 1 electron because it's a metal, and we form sodium ion. Chlorine has the 7 valence electrons. It's a nonmetal, so it's going to become negative, so it's going to gain that electron. So the electron from sodium, where it's going, is to our chlorine. Once it gains that, we get chloride negative, and we have a total, again, 8 valence electrons for both of these. So it's that transfer of electrons that actually creates the bond between opposite charges. Now, ionic compounds, they form between metals and nonmetals, because metals, we said, form positive ions or cations, and nonmetals form negative ions or anions. And opposites are attracted to each other, and that's what creates an ionic bond. Ionic compounds are electrically neutral. The positive and the negative charges are attracted to each other in equal ratios so that the charges will cancel each other out and will end up with a neutral charge. Ionic compounds are not distinct molecules, but they're actually just a ratio of ions. For example, if I have sodium ion and chloride ion, we said they're attracted to each other because of that electron transfer between the sodium to the chloride, and we end up with sodium chloride as our ionic compound. So this is showing us at the molecular level that we have this ratio. Here's a chloride ion to a sodium ion, and this is a 1-to-1 ratio, and it forms this crystalline lattice structure here. So this one is showing us the negative charges are the chlorides, the positive are the sodium. So it's a 1-to-1 ratio, and when it forms this crystalline structure, this is what pure table salt, sodium chloride, would look like, is this pretty crystal structure. Ionic compounds, we just said, were neutral. And we can actually predict ionic formulas by making sure that our charges will cancel each other out. Now, there is sort of what I say a shortcut way to do this, and that's what we're going to follow in these steps. So the first one says just write down the symbol and the charges of your cation and your anion. So if I was to give you the name calcium ion, you know its ion symbol would be Ca and a superscript 2+. And if I told you we had chloride ion, we would know that would be Cl-1. Now, to predict the ionic formula formed from calcium ion and chloride, what we're going to do is we are going to do what we call crossing the charges. So we take the subscript in calcium, the 2+, and we have a subscript, the charge in chloride, and what we're going to do is cross the charges from one element to the other. So I rewrite the element symbols below. So I wrote calcium and chloride down below. And now I take the 2 at calcium and I bring it down and make a subscript. And with the chloride, it's a -1. I would bring that 1 down here. So this is what we mean when we say cross the charges. So the charge of the cation will become the subscript of the anion, and the charge of the anion becomes the subscript of the cation. So if you have a negative value for your ion, what the subscript tells us is the number, in this case, of ions of each element we have. So we can't have a negative quantity of ions, so it always has to be changed into a positive. And if you have just one ion in your ratio of ions, you don't have to show it. So you could just write CaCl2. That's my ionic formula. Now we can actually check to make sure that our charges cancel out and we have a neutral ionic compound. So calcium, we said, has a +2 charge. In my formula, I had a subscript of 1, so I'm going to have 1 times +2 gives me +2. I have, in my formula, I have 2 chlorides, so I end up with 2. The charge on my chloride was -1. 2 times -1 gives me -2. I add my 2 charges together, +2 -2, and I get a net charge of 0. So I have a neutral ionic compound, which is what we're after. You can also sort of visualize this if you wanted to. We said we have 1 calcium ion and 2 chloride ions. Each chloride ion has a -1. So my overall charge, if I add these two together, is a -2. So the -2 charge balances the +2. So this crossing the subscripts is is a shortcut way to determine your ionic compound. Our last rule in writing ionic compounds is to remember that all subscripts must be reduced to the lowest term. So let's go ahead and create our ionic compound. Here we have zinc ion, and we're going to take the charge and make that the subscript. And an oxide, the same thing. I'm going to cross the charge. We have a -2, but we never have a negative value, so we put a 2 here. So I have Zn2O2. Now this rule is saying reduce to the lowest possible ratio. So our ratio is 2 to 2. We have 2 zincs to every 2 oxides. Well, we can reduce 2 to 2 to 1 to 1. So that's what they mean in this one. If you end up creating an ionic formula that you can reduce further, you must do that. You can never have a fraction. You couldn't have like 1.5, anything that was a fraction, because you don't have a fraction of an ion or a fraction of an atom. So our formula for this, once we reduce our ratios, would be 1 to 1. The ones, again, you don't have to show them. We could just write ZnO. And this is called zinc oxide, and this is the material that protects you from the sun. So that's the white compound on this gentleman's face. To check our charges, again, in our formula we created, we have 1 zinc times its charge of +2, we have a +2. We have 1 oxide times the charge of -2, gives us -2. +2 minus 2 is 0, so we have a neutral ionic compound. What is the compound formed from sodium ion and iodide ion? The first thing we want to do is write down the ion symbols. So sodium we know is Na. It's in column 1, so its charge is +1. Iodide is I-. This is not one of the ones you have to remember, so I would actually give you the ion symbol for that one. Iodine is one of our halogens. It's in column 7, so it has a -1 charge. So we're going to rewrite our element symbols again. We're going to cross our charges. We have a +1, so the subscript becomes 1. We have a -1 on the iodide. Our subscript for sodium becomes 1. And again, we don't have to show the ones. We can write NaI, and that's my ionic formula. If I want to check the charges, again, for sodium, I have 1 sodium with a +1 charge. This is 1 times +1. And we have 1 iodine, so 1 times -1. So we end up with +1 minus 1. Net charge is 0. What is the compound formed from magnesium ion and chloride ion? Okay, magnesium is Mg. It's in column 2, so it forms a +2. Chloride is Cl. It's in column 7, so it forms a -1 charge. We rewrite our element symbols, and then we cross the charges. So my superscript, the +2, becomes a subscript of 2 behind chloride, and the -1 becomes a 1 behind the magnesium. Again, we don't have to show the 1, so we have MgCl2. Now, if we want to check the charges cancel, again, we can say magnesium. We have 1 magnesium times its charge of +2 gives me 2 plus. And then chloride, we have 2 chlorides. Each chloride has a -1, so it becomes -2. Plus 2 minus 2 is equal to 0. So we have a neutral ionic compound. Does carbon form ionic compounds? The answer is no. Because we said carbon is one of the exceptions, carbon does not form ions. So if there are no ions present, you can't form an ionic compound. Carbon is going to form a different kind of bond with other elements called a covalent bond. Covalent bonds occur when two atoms share a pair of electrons between themselves. That creates what we call a covalent bond. Covalent bonds form between nonmetals, versus ionic was between a metal and a nonmetal. Covalent is between nonmetals. So for example, we have hydrogen here. We have its Lewis dot structure where the dot represents the valence electron, or the electrons in the outermost shell. So here I have a picture drawn of hydrogen with 1 valence electron. Again, remember it's 1s1. Atomic number is 1. We have another hydrogen. They each have 1 valence electron. In order for them to be stable, they want to have 2. And so sharing these 2 electrons, as drawn with the arrow here, this picture is probably showing it better down here, you can see the 2 electrons are being shared between each hydrogen. Now the hydrogen, oh, I'm happy, I'm stable, I'm just like helium with 2 valence electrons. So this is showing that this hydrogen thinks I'm like a helium, and this hydrogen says, hey, I'm just like helium too. So now we have a stable molecule, H2. And this represents the 2 dots sharing in between the 2, our valence electrons, represents the covalent bond. And we learned 7 diatomic elements, the have no fear of ice cold beer. H2 is one of our diatomic elements. So H2 is why you find hydrogen in nature is more stable as H2 versus a single atom of hydrogen, because of its outermost shell of electrons being full. Covalent bonds can be broken down into discrete or distinct molecules, as what's shown in the picture here. The line represents the bond, so that's the covalent bond between our 2 hydrogen atoms, versus an ionic bond was the transfer of electrons, and it's the charge attraction to each other that holds them together. These are actually representing 2 electrons being shared between atoms. That's our covalent bond, and they actually create these distinct individual molecules. Chlorine is a nonmetal. If I have 2 atoms of chlorine, I have the Lewis dot structures represented here, showing me their valence electrons. They each have 7. They want to have 8 to be stable. So chlorine, again, is one of our diatomic elements. It doesn't exist as chlorine atom. It's always going to want to bond with something else. So in this case, chlorine exists as Cl2 as a molecule because these 2 atoms of chlorine can come together and share 2 electrons. Now each of these chlorines think, I've got 8 electrons. Following the octet rule, I'm going to be stable as a molecule of Cl2. And again, we can look at the electron configuration down here. So neon represents all of the core electrons, okay, which is represented here. We have our nucleus of chlorine in the middle, and then 1s with 2. We have 8 electrons in the 2. Energy shell, our outermost shell, has 7, and that's in energy level 3. So when they come together and they share the electrons, it's the outermost electrons, again, is where the bonding is occurring. Now we have the outermost shell 3 with 8 valence electrons. So now our chlorine molecule is stable due to its covalent bond. Lewis structures, also known as Lewis dot structures, show your outer shell or your valence electrons. The ones that are not bonding are shown as dots, and The electrons that are being shared, or your bonding electrons that represent your covalent bonds, are drawn as lines. So for example, we looked at hydrogen. It was sharing one electron from each hydrogen. This represents the bond. So we draw that as a line. The chlorine molecule here, these electrons that are not attached to anything else are called our non-bonding electrons. The ones that are the bonding electrons, which are the ones that are being shared between two atoms, are drawn as a line. We can determine the number of bonds our nonmetals form based on their Lewis dot structures. So for each nonmetallic atom, it has a strong tendency to form a particular number of covalent bonds. So let's start with our nonmetals in column 8, our noble gases. They have 8 valence electrons, as you can see in neon. So that would be for our entire column. So the number of bonds they form is 0 because there's no place for anything to bond to. It's already got a complete outer shell as electrons. So in our picture here, you can see for neon, shell 1 is full with 2. And again, we're only looking at the outermost shell and valence electrons. This one has 8 electrons. Now, if we go to column 7 and we look at fluorine, fluorine has 7 valence electrons because it's in column 7. And if we look at our atom of fluorine drawn here, we're only looking again at the outermost shell. We have 2, 4, 6, and then we have this 1 electron by itself. So if I wanted to share an electron with someone else, it only has space to share with one other atom, which would be where this electron could share. So the number of bonds that the halogens form in column 7 is 1. If we go to column 6, we have an example here of oxygen. Its Lewis dot structure is drawn, and the picture of the atom is above, and at the top we have 2 electrons here, and then we have singles on each side here. So where these single electrons are would be space for this electron to share with another atom of a different element and form 2 bonds. So column 6 elements form 2 bonds. So it's not just the elements represented here. Realize this is the whole column of elements. In column 5, they have 5 valence electrons. Okay, so I have a picture of nitrogen up here, and again we have 2 electrons at the top, but on the other sides we only have 1. So nitrogen has the potential to share with 3 other atoms and form 3 covalent bonds. Carbon is the last nonmetal we'll be looking at here. Carbon has in its outermost shell 4 valence electrons. So the Lewis dot structure is drawn with 4 dots around it, which means carbon can form 4 bonds. So column 4 for our nonmetals would be 4 bonds. So you want to know the number of bonds that these nonmetals can form, because we're only going to be looking for covalent compounds, which are going to be for nonmetals. So some of our nonmetals can form what we call double bonds. When we looked at oxygen, we said oxygen can form 2 bonds. So oxygen can form 2 single bonds. For example, in water, we have H2O. Oxygen is bonded to 2 hydrogens. Both of those are covalent bonds. But oxygen can also form what we call a double bond, which is shown in the picture here. So a double bond is where we share 2 pairs. So remember again, if I had oxygen bonded to an oxygen, each line represents 2 electrons. So that's a pair of electrons. I can actually move another pair of electrons here to the center and create what I call a double bond. So in the picture down here, this is showing me my Lewis dots, that I'm sharing the electrons between these 2 oxygen atoms. And anytime you're sharing electrons, we have 2 dots, it's represented with a line. So this is a double bond. The double bonds are actually going to be stronger and shorter than single bonds. So this again represents our double bond. So whenever we're sharing a pair of electrons, we draw that as a single line. single bond. If there's two of them, two pairs represents the double bond here. And so double bonds again are going to be shorter than a single bond. So if I wanted to say this is a single bond, my double bond would be shorter than that. So you actually have powerful microscopes that can measure the distance between the atoms to determine the length of the bond. So double bonds are shorter than single bonds. The other thing is they're stronger. I like to imagine if I had a piece of wood and I was taking karate and my instructor said I need to cut that in half. And if I had a very long board and I tried to cut it in half, it's probably going to be easier to cut in half than if I had two shorter boards. So I always think of that kind of analogy here is that two shorter boards, if they were right next to each other, it's going to be much harder for me to use my hand and chop right through that. Elements that can form 3 or more bonds can form what we call triple bonds. So for example, nitrogen is in column 5, so it could actually form 3 single bonds, or maybe nitrogen might form a double bond and a single bond. It's always going to have 3 bonds, but it can also form what we call a triple bond. And what a triple bond is when we have 3 electrons pairs being shared between atoms. So in nitrogen here, this first 2 dots between the 2 nitrogen atoms would be a single bond. But we can move these electrons into the center and share them as well, which is represented down here. So we have 3 pairs of electrons being shared between atoms. We call that a triple bond, and we would represent it with 3 lines. Again, each line represents 2 electrons. So this again shows us an example where we have N2, one of our diatomic elements that actually has a triple bond in it. And again, the pairs of electrons represent the bonds. So we have a triple bond represented with 3 lines. This slide shows us the distance between single, double, and triple bonds, and also the strength. So our first box here, you can see the length is longer for our single bond versus the second one down, our double bond, which we mentioned. Now our triple bond is even shorter. And then also the strength. So going back to my karate analogy, if I had 3 boards that were shorter than a longer single board or 2 double ones, that's going to be even stronger. So triple bonds are the strongest and the shortest. In order to draw Lewis structures for covalent compounds, we have a set of rules we need to follow. Rule number 1 is, first of all, I have a molecular formula written here, is to find out how many atoms I have of each kind of element or in my molecule. So in H2O, the subscript tells me the number of atoms I have. So I have 2 hydrogens, oxygen, there's nothing written behind it, so it's implied that it's 1, and we have 1 oxygen. Rule number 2 is to write the Lewis dot structure for each atom. So Lewis dot structure is going to be equal to the group number for the number of valence electrons. So for hydrogen, it would be in column number 1, has 1 valence electron. So again, they each have 1 valence electron. Oxygen is in column number 6 on our periodic table, so it has 6 valence electrons. So these are our Lewis dot structures for our 2 hydrogen and oxygen. We want to know the total number of valence electrons for our molecule, so we just add those up. So we have 1 plus 1 plus 6. We have 8 valence electrons for our molecule. Rule number 3 is to write the skeletal structure for the molecule. So the skeletal structure is determining which atom is going to be the center and what's going to be on the outside of that center atom. As a rule of thumb, hydrogen is always going to be placed around the central atom because hydrogen can only form 1 bond. We can also say our halogens always form only 1 bond. So halogens will also be on the outside, placed around your central atom. And if we look at oxygen, oxygen we know can form 2 bonds. So if the more bonds your element can form, then that's the one that's going to be in the center. So oxygen needs to be the center between our hydrogens. Rule number 4 is to insert electrons into the skeletal structure. we're going to be following the octet rule, so we'll have 8 electrons per atom in order for that atom to be stable, unless of course it's hydrogen, which is stable with a duet, or 2 electrons. So there's a set of rules that we need to follow as far as the order of which electrons do we start with. The rule is we always start with the bonding electrons. So our total amount of electrons we had for this molecule was we had 8. Okay, so we have 8 electrons that are going to go into this molecule. The first electrons are always going to be bonding because this molecule wouldn't exist unless our atoms were bonded together. So the first electrons we're going to be adding in here are the bonds between hydrogen and oxygen. So we add those in, we've used 4 electrons. Then we're going to add lone pairs on the outer atoms. So the outer atoms would be hydrogen versus the center atom, which is oxygen. Now hydrogen, we said, is stable with the duet. So our hydrogens are already stable, we're not going to add any electrons there. Our oxygen, however, has a total, when we look at it right now, as circles, we have 4 electrons. We've used up 4 electrons when we did the bonding electrons, so we have 4 electrons left. So now we're going to add the electrons on the center atom. So that's these 2 at the top and these 2 electrons at the bottom. So the electrons that are not bonding to anything is what we call lone pairs. So our oxygen has 2 lone pairs of electrons. Now rule number 5 says draw lines for all bonding electrons. So the 2 dots between our oxygen and hydrogen represent our bonding electrons. We drew those as lines down here. So that would be my Lewis dot structure for a molecule of water. And just going back to terminology again, the lone pairs electrons, the ones that are not bonding, are at the top, and we have a pair of non-bonding electrons at the bottom. The electrons that are shared between our atoms are called bonding electrons. So if I asked you for water, how many bonding electrons does it have? Total amount of bonding electrons would be 2 plus 2, gives me 4 bonding electrons, or you may say 2 pairs, because a pair is 2 electrons. If I asked you for non-bonding electrons, we would just count those up, and we would have 4 non-bonding electrons, or 2 pairs as well. Draw the Lewis dot structure for a molecule of fluorine. So the first thing is determine the number of atoms of fluorine we have, which is our subscript. So we have 2 fluorines. Next, we're going to draw the Lewis dot structure for each fluorine. So I'm drawing my 2 fluorines. Fluorine is in column number 7, so therefore fluorine has 7 valence electrons. So I'm doing the Lewis dot structure for my individual atoms of fluorine. Now I want to total the amount of valence electrons I have for my molecule. So we have 7 plus 7 gives me 14 valence electrons. Now in this case, to put my skeletal structure together, I don't really have any options except fluorine bonded to fluorine. Now our rule says is the first 2 electrons we're going to insert are going to be our bonding electrons. So 2 electrons here represent the bond between fluorines. Next, we're going to put in the non-bonding electrons, and we go to the external atoms, which are both fluorines. So we've used up 2, so we have 12 valence electrons left to use in our molecule. So let's start adding. Each atom wants to have 8. So I added 6 to this fluorine, and it had 2 in the center, so this fluorine is happy with 8. I've used 6, I have 6 left. So I'm going to put 6 on this other fluorine. Now both of our fluorines have 8 valence electrons, so it looks pretty stable. The last thing we need to do in our Lewis dot structure is the 2 dots that represent the bonding electrons need to be drawn as a line. So I'm changing that into a line, and I'm showing all of my non-bonding electrons. So this would be my Lewis structure for a molecule of fluorine. This slide shows the formation of a fluorine molecule from two fluorine atoms. You can see that the electrons being shared in the center in the white spheres represent our bonding pair of electrons. The electrons that are not being shared between the two atoms are called our lone pair of electrons or our non-bonding electrons. Draw the Lewis dot structure for CCl4, also known as carbon tetrachloride. We're going to start by determining the number of atoms of each element. So we have 1 carbon and we have 4 chlorines. Then we're going to do the Lewis dot structure for the individual atoms. Carbon is in column 4, so it has 4 valence electrons. Chlorine is in column 7, so it has 7 valence electrons for each one of our chlorines. All right, we're on our last chlorine with 7. We want to count the total number of valence electrons. So we have 4 for carbon plus 7 for chlorine. There's 4 chlorine, so let's just multiply 7 times 4, which is 28. So we have 4 plus 28 gives me 32 valence electrons total. Now to put our skeleton structure together, carbon can form 4 bonds. Chlorine has 7 valence electrons. It can only form 1 bond. So if I can only form 1 bond, that's always going to be the external atom. Carbon can form 4 bonds. That needs to be in the center. The element that can form the most amount of bonds will always be in the center. So we're going to surround carbon with 4 chlorines. And now we're going to insert our electrons following our rules. They first say bonding electrons. So let's draw our bonding electrons. Again, our 2 dots between atoms represents our covalent bonds. Next comes the non-bonding electrons. And they go on the external atoms first. So we're going to start with our chlorines. And we're going to add electrons so that the chlorine gets 8 electrons. Our carbon in this molecule already has 8. So let's see if we count that they all have 8. Okay, so right now chlorines have 8, carbon has 8, and we should have used 32 electrons. So let's just count to make sure. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we used our 32 valence electrons up. The last thing we need to do is all of our bonding electrons need to be drawn as lines. So let me redraw our molecule here with lines to represent the bonds. And then you also have to show all those non-bonding electrons around the chlorine. And once that's done, we will have our Lewis dot structure for carbon tetrachloride appropriately written here at the bottom. Draw the Lewis dot structure for nitrogen triiodide Ni3. So we have 1 nitrogen and we have 3 iodines. Nitrogen is in column 5, so we have 5 valence electrons. Iodine is in column 7, so we have 7 valence electrons around each one of those iodides. And then we're going to count our total number of valence electrons. So we have 5 plus 7, and we have 3 of them. 7 times 3. So we have 5 plus 21. We have 26 valence electrons. Now we're going to put our skeleton structure together first. The skeletal structure is based on the number of bonds that can form the most is the element that goes in the center. So nitrogen has 5 valence electrons. It can form 3 bonds. Our halogens, our iodine, have 7 valence electrons, so they can form 1 bond. So the one in the center, you guessed it, is going to be nitrogen because it can form more bonds than the iodine. Nitrogen will be surrounded by our iodines. And now we're going to insert our electrons. The first electrons are always inserted as bonding electrons. So we're going to add a bond between the nitrogen and the 3 iodines. Next, we're going to add the electrons on the outermost element. So 1 is bonding electrons. 2, we insert non-bonding on outermost elements. And then 3, we put non-bonding on the center element. Okay, so it's important to follow this order. All right, so we've added 6. We've got 20 electrons left. So we're going to go on our outermost electrons next. Outermost atoms, excuse me. The iodines. I'm adding 6 to each one of these, so then they have a total of 8. So at this point, I've added 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 electrons left. Now I put my electrons on my center atom, because I have 2 left, and then I check. Does everyone have an octet? The iodines each have 8, nitrogens have 8. It looks stable. So the last thing is to connect my electrons that are the bonding ones, and I'm just going to erase what I have here because I don't have very much room on my page, and insert a line. And now I have my Lewis dot structure for nitrogen triiodide. Rule number 6 in writing Lewis dot structures for covalent compounds is to form double or triple bonds if your atoms do not have 8 electrons around them. So let's do the Lewis dot structure for CO2 or carbon dioxide. So we have 1 carbon and we have 2 oxygens. Carbon is in column 4, so we have 4 valence electrons. Oxygen is in column 6, so each oxygen is going to have 6 valence electrons. So if we count our total electrons, we have 4 plus 6 plus 6 gives me 16 valence electrons. Now for my skeletal structure, carbon can form 4 bonds, oxygen can form 2 bonds. So the one in the center is going to be carbon, and then we're going to have oxygens outside of carbon. Now following our rules, the ones that go in first are always bonding electrons. So I put in some bonding electrons. And then secondly, I put non-bonding, but I put them on the external atoms. So I'm going to give each oxygen, I'm going to add 6, so each oxygen now has 8. So let's count how many electrons we've used so far. So we have 2, 4, 6, 8, 10, 12, 14, 16. Now when we look right now, we've used all of our valence electrons. So we can't just go ahead and write a couple more dots around our carbon to give it an octet. We've used up all of our valence electrons. So this is when we go to rule number 6, that we're going to need to form, a double or a triple. We start with double bonds first. So carbon is not happy because it only has 4 electrons. Oxygens are good, but oxygens are willing to share with carbon. So I can take a pair of electrons and move those to the center between my carbon and oxygen. And when I do that, oxygen still has 8. It's got this 2 pairs between the carbons and then the 2 lone pairs. So this oxygen has 8, it's good. Carbon though only has 6 still. So we're going to take another pair of electrons and move those to the center between my carbon and my oxygen. Now when I do that, my oxygen has 8 and now my carbon has 8. So this is now going to be a stable molecule. And what I've done is I've created 2 double bonds. So I need to show that. So let me draw my pairs of electrons as double bonds between my carbon and oxygens. And then I'm going to show the non-bonding electrons on the oxygen atoms. So it's only when you don't have an octet around your atom that you're going to create a double or triple bond. This table shows some general differences between ionic and covalent bonds. Ionic bonds are the transfer of electrons from one element to another, which results in the charges. For example, in sodium, we create sodium ion, and chlorine becomes chloride ion. We have a transfer of electrons to create those ions. Covalent bonds are when we share electrons. For example, we said when we create oxygen, we share electrons between the two oxygen atoms to create a covalent bond. Ionic bonds are going to be between metals and nonmetals. Again, for example, sodium is a metal and chlorine is a nonmetal. Our covalent bonds are between nonmetals and nonmetals, just like an oxygen bonded to oxygen. Those are two nonmetals. Ionic bonds are a ratio of ions. Okay, they're not a distinct molecule. This is showing us the ratio of sodium ions to chloride ions in that ionic compound, versus covalent bonds form distinct molecules. Do these compounds have ionic or covalent bonds? We can determine that by the type of element we have. So sodium is a metal and fluorine is a nonmetal, using our periodic table, and bonds between metals and nonmetals are ionic. So sodium fluoride has ionic bonds. Carbon is a nonmetal. Hydrogen is a nonmetal. And oxygen is a nonmetal, and is our other hydrogen. So all these nonmetals bonded together create a compound that includes covalent bonds. The ions we've talked about so far have all been monatomic ions. For example, Na+. That's an ion and it came from one atom. Ions that contain more than one atom are called polyatomic. Poly means many, so two or more. So there are 6 polyatomic ions that I want you to remember. The first one is hydroxide ion. Its symbol is OH-. You need to know the name and the ion symbol. So what this means here is we have an oxygen bonded to a hydrogen, and then I have brackets around it. It's got a negative charge. That means we have an ion, but the -1 charge is on this whole unit. This is what makes it a polyatomic ion. It's not the way it looks at the one above, that the -1 is on the hydrogen. It's on the whole unit. Ammonium ion is the second one you need to remember. So know the name, and then the formula is NH4+. So I've drawn it down here below to show you it's a nitrogen bonded to 4 different hydrogens. The +1 is on this whole unit. So again, this +1 is not just on the hydrogen, it's on this whole unit here. So this slide shows you the 6 polyatomic ions I want you to remember. There's many more polyatomic ions than what are listed here, but these are the 6. I want you to remember the names and the symbols. So as we mentioned previously, we have hydroxide ion, which is OH-, ammonium ion, which is NH4+. This is the only polyatomic ion that you have to remember with the plus charge. Next we have nitrate, which is NO3-. We have carbonate, CO3, 2-, sulfate, SO4, 2-, and phosphate, PO4, 3-. So you do need to remember those ion symbols. You need to know the correct charges for the superscripts, and remember the subscripts that tell you how many oxygens or hydrogens you have. Now I have a trick to help you remember the polyatomic ions that end in 8. So those were the last 4 out of the 6 to remember. They all end for their name in 8. So you had nitrate, carbonate, sulfate, phosphate. And then you need to know the polyatomic ion symbol. And these are ones that students sometimes make mistakes in remembering what is the charge and how many oxygens are in that polyatomic ion. So this sentence is very helpful to help you remember. The sentence is, Nick the camel ate supper in Phoenix. And how this works is the word we have in the front, the name Nick. Notice when it's drawn down here, the consonants are written in red and the vowels are written in blue. The consonants represent the number of oxygens that are going to be in your polyatomic ion. So if we look at the word Nick, it has 3 consonants. So we have 3 consonants here, and our polyatomic ion has 3 oxygens in it. And then the vowels, the I, represents the charge. So we have one vowel, so it has a -1 charge. So nitrate has a -1. Camel has 3 consonants as well, so it means it has 3 oxygens in its polyatomic ion. It has 2 vowels in blue, so the charge is going to be a -2. All these charges are negative, so carbonate has a -2. Supper, we have 4 consonants, so that means we have 4 oxygens as my subscript. And then we have 2 vowels, so our charge is -2. Phoenix has 4 consonants, so that means we have 4 oxygens as my subscript. And then I have 3 vowels, so I have a charge of -3. So I recommend learning this sentence to help you know these 4 polyatomic ions. We can write ionic formulas using polyatomic ions. We're going to follow the same rules we did before with crossing the charges. So what is the compound form from calcium ion and hydroxide ion? So the first thing is to write the ion symbol. So calcium is Ca. It's in column 2, so it has a 2+. Hydroxide ion, this is where the part comes in where you have to memorize those polyatomic ions. It's OH negative. Now we're going to rewrite our element symbols again. And now we're going to be crossing the charges. The only difference when you do a polyatomic ion is, remember, the polyatomic ion is a unit. So you're going to put parentheses around our polyatomic ion. And when you cross the charge, so the superscript, the 2, becomes the subscript behind the hydroxide, we put the 2 outside the parentheses. And then hydroxide is a -1, and then a 1 would go down there. And again, when we write our formula, we don't have to show that 1. So it's just Ca parenthesis OH2, and that would be calcium hydroxide. Now I want to point out it's very important to have the parentheses. So if I just wrote CaOH2, that would imply that I have 2 hydrogens and only 1 oxygen. By having parentheses, that means multiply by everything on the inside. So this is showing me that I have 1 calcium ion with a 2+ charge, and I have 2 hydroxide ions, because that's a unit. Each hydroxide ion has a -1. So if I wanted to balance my charges here, I could see a -1 plus a -1 gives me a -2. So the +2, -2 makes this a neutral ionic compound. What is the compound form from sodium ion and carbonate ion? So the ion symbol for sodium is Na. It's in column 1, so it's a +1. Carbonate is the polyatomic ion you need to memorize. It's CO3 2-. Again, you can think of camel to figure out the number of oxygens and the charge. So we rewrite our symbols below, and then we're going to cross our charges. So we can put parentheses, and then sodium has a +1, so a 1 goes behind the carbonate. Then the 2 from the carbonate goes as a subscript next to sodium. Now in this case you have a 1 outside the parentheses. The number outside the parentheses means multiply by everything on the inside. So if it's a 1, we don't really have to show that parentheses. So we can just write Na2CO3. And again, we can check that our charge is balanced. We can look at our formula we created. Each sodium has a +1, and there are 2 of them. And the carbonate has a 2-. So the 2 sodiums added together gives me a +2, which cancels the -2, giving me a neutral ionic compound.